Hello students, in Physical Pharmaceutics 1 lecture series, today's topic is solubility of drugs. And in this unit of solubility of drugs, today we have to discuss about the different parameters like ideal solubility parameters, solvation and association, and then quantitative approach to the factors influencing solubility of drugs. So these are the learning objects of today's topic. So to study or to learn about the concept of solubility of drugs, ideal solubility parameters, then solvation, then quantitative approach to the factors affecting solubility of drugs with suitable examples. After completion of today's lecture, I hope students will be able to know about concept and significance of solubility of drugs. They can learn about the ideal solubility parameters. They can know the solvation and association phenomena and understand the quantitative approach to the factors influencing solubility of drugs with different examples. Now, in introduction of solubility, so in previous lecture regarding the solubility expression and mechanism of solubilization, we discussed about the solubility can be defined is quantitative way as well as the qualitative way. In qualitative way, the amount of solute that can be dissolved in 100 gram of solvent at a specific condition, it will be known as solubility. Similarly, in quantitative terms, it can be defined as the interaction between the solute and solvent molecules. More interaction, more will be the solubility. So, qualitative and quantitative way we can define the solubility, and it is very important physical phenomena where the dissolution, the absorption, the bioavailability of different drugs depends on this phenomena. So solubility is the maximum dissolved concentration under given solution conditions. Solubility is a determinant of intestinal absorption and oral bioavailability. Solubility is increased by adding ionizable groups or reducing by low P is partition coefficient and molecular weight of particular compound. And when we use the salt form of drug, they can increase the dissolution rate and increase the solubility of the drug. So solubility is very important parameter. So at the time of formulation part, first we have to study about the solubility of given drug. If the drug is less soluble or poorly soluble, then we have to use the different methods for enhancement of solubility. Because until and unless the drug is solubilized, it cannot reach into the systemic circulation and cannot show the therapeutic effect or pharmacological effect. So, the solubility of drug is very, very necessary for all the compounds. So, what are the different effects which can be seen if the drug is poorly soluble or having low solubility? Let us see here. So, many negative effects can occur for low solubility compounds, is poor absorption and less bioavailability after oral dosing, insufficient solubility for intravenous dosing, then artificially low activity values from bioassays. Erratic assay results can be obtained due to the low solubility compound, maybe biological or other methods. Then development challenges, like expensive formulations and increased development time. Then burden shifted to patient like frequent high dose administrations required. So these problems or these different aspects can be seen with the drug having less solubility or poor solubility. So many negative effects can occur for low solubility compound, and some of the effects are given here. Now, as we know, there are different terms to express the solubility of a pharmaceutical compound. So ideal solubility parameters. So as we know, ideal solubility parameter, which can be denoted by delta, is known as Hildebrand solubility parameter, which provides a numerical estimate of the degree of interaction between materials and can be a good interaction of solubility, particularly for non-polar materials such as many polymers. So materials with similar solubility parameter value or delta value are likely to be miscible. So if we know or if we determine the solubility parameter value and we know the similarity between the different solubility parameter of different compounds, we can predict that they can be easily miscible in each other. So Hildebrand solubility parameter. So when we go through the discovery of this solubility parameter, we can find the very important name. This is the John H. Hildebrand in 1936, who laid the foundation for solubility theory in his classic work on the solubility of non-electrolytes in 1916. Proposed the square root of the cohesive energy density as a numerical value indicating the solvency behavior of a specific solvent. So solubility parameter or Hildebrand solubility parameter is the square root of the cohesive energy density as a numerical value which indicates the solvency behavior of a particular solvent. So until the third edition of his book in 1950, the term solubility parameter was proposed for this value and the quantity represented by the symbol psi. Subsequent authors have proposed that the Hildebrand be adopted for solubility parameter. So in order to recognize the tremendous contributions that Dr. Hildebrand has made to solubility theory, so the name was given as Hildebrand solubility parameter. So ideal solubility parameter, which is also known as Hildebrand solubility parameter. So Hildebrand solubility parameter is the square root of the cohesive energy density. The cohesive energy density is nothing but it is the amount of energy needed to completely remove unit volume of molecules from their neighbors to infinite separation, like in ideal case. So definition of cohesive energy density, it is the amount of energy which is needed to completely removal of unit volume of molecules from their neighbors to infinite separation. This is equal to the heat of vaporization of the compound divided by its molar volume in the condensed phase. In order for a material to dissolve, these same interactions needed to be overcome as the molecules are separated from each other and surrounded by the solvent. So for material to dissolve, these same interactions needed to be overcome when the molecules are separate out from each other and then it will be surrounded by the solvent. So cohesive energy density, this is equal to the heat of vaporization of the compound divided by its molar volume in the condensed phase. And in 1936, Jules Henry Hildebrand suggested that the square root of the cohesive energy density is a numerical value indicating solvency behavior. To express the solvency behavior, he prescribed the ideal solubility parameter, which is known as Hildebrand solubility parameter. This later became known as the Hildebrand solubility parameter. Materials with similar solubility parameters will be able to interact with each other resulting in form of solvation, miscibility or swelling. So as we earlier discussed about the process of solubilization, and when we go through the mechanism of process of solubilization, we know that if there is more interaction, then there will be the more solubility. So solubility parameters will be able to interact with each other, and if the solubility parameters are similar for different compounds, they can easily miscible in each other. So mathematically, when we go through the formula for this Hildebrand solubility parameter, so strength of non-polar solvents are described by Hildebrand solubility parameters. So there are two type of parameters are given. One first Hildebrand solubility parameter, which is denoted by delta 1 is equal to alpha by V 1 by 3, where alpha is the surface tension of the compound, V is the molar volume. And second Hildebrand parameter, which is based on cohesive energy density. So delta 2 is equal to delta E divided by V to the power 1 by 2. So delta E is energy of vaporization and V is the molar volume. So delta E equal to delta HV minus RT, where delta 2 is combinedly denoted like delta HV minus RT divided by V 1 by 2. So enthalpy of vaporization can be known as delta HV. V is the molar volume, delta E is the energy of vaporization, R is the gas constant, and T is the absolute temperature in this equation. So by going through this equation, we can determine the Hildebrand solubility parameter. Now, after the discussion of Hildebrand solubility parameter, which show the interaction between different compounds. So, if the interaction is more or similar in nature, then the solubility will be more, and the compounds having similar solubility parameter can easily solubilize or can be easily miscible in each other. Now, after the solubility parameter, solvation and association process or mechanism. So, by an IUPAC definition, solvation is an interaction of a solute with the solvent. If the solvent is water, then it will be known as hydration. So, it is interaction of a solute with the solvent molecules, which leads to stabilization of the solute species in the solution. So, when solute interact with the solvent, it will be led to stabilization of the solute species in the solution. The solvated state in ion in a solution is surrounded or complexed by other solvent molecules. In solvation or dissolution, it is a kinetic process and it is quantified by its rate. When we go through the association mechanism, very important phenomena which is known as Van 't Hoff factor. So Van 't Hoff introduced a factor I called Van 't Hoff factor to express the extent of association or dissociation of the solutes in solution. So on the basis of Van 't Hoff factor, we can calculate the extent of association or dissociation of a particular solute in solution. Now, degree of association, which is known as A, it is defined as the fraction of the total number of the molecules which associate or combine together, resulting in the formation of a bigger molecules. So, degree of association is defined as the fraction of the total number of molecules which can associate or combine together, resulting in the formation of a larger molecule or bigger molecules. So it is known as association, and the extent of this association is known as degree of association. So solvation and associations are very important mechanisms where they can show the interaction between the solute with solvent molecules. Now solubility is determined by many factors. like compound structure of a particular compound, then physical state of compound that is introduced into solution. Either it may be present in the solid form, like amorphous form, crystalline form, or polymorphic form. And it may be present in the liquid form, like pre-dissolved in solvent, DMSO, dimethyl sulfoxide. Depends on the composition and physical condition of the solvent, or maybe more than one solvent. So depends on the types of solvents, amount of co-solvent or percentage of co-solvents, solution components like salts, ions, proteins, lipids, or surface active agents or surfactants, then pH and the temperature. So these are the different composition and physical conditions of solvent which also affects the solubility. Then methods of measurement is equilibration time, separation technique, either it may be through filtration or centrifugation, or detection technique, maybe UV, ultraviolet technique, maybe mass spectrophotometry, or maybe turbidity. So these are the different factors which affects the solubility also. Then when we go through the special structural properties that affects the solubility, like the lipophilicity of drug, which can be determined by the help of partition coefficient determination. It can be also determined by van der Waals, dipole hydrogen bonds, ionic interactions, etc. So it depends on the nature of the particular compound. Similarly, size of the particular compounds like molecular weight, shape, etc. So peak molecular weight, shape, they can affect the size. The size also affects the solubility of particular compound. Then when we go through the ionization process, we can say that the pK is determined by functional group ionizability. So pK is the ionization constant, which depends on the ionization or degree of ionization can be governed, can be regulated by this type of pKa constant. Then crystal lattice energy can be determined by crystal stacking or melting point. So these are the different structural properties which affects the solubility of a particular compound. Next one, after it, there are two types of solubility. Either it may be kinetic stability or maybe thermodynamic stability. So when we go through the different type aspects of solubility, either it may be kinetic stability, solubility or thermodynamic solubility, we can find different characteristic features and different usage also. So when we go through the characteristics of kinetic solubility, we can find that the compound initially is fully dissolved in an organic solvent like DMSO, dimethyl sulfoxide, then added to the aqueous buffer. And in thermodynamic stability, the addition of aqueous solvent directly to solid crystalline material. Then in kinetic solubility, the equilibrium is not reached between dissolved compound and solid compound, like metastable, amorphous or mixture form can be obtained. And in thermodynamic stability, the establishment of equilibrium between the dissolved and solid material and original condition can be obtained. When we go through the different usage of kinetic and thermodynamic solubility, we can find that the kinetic solubility, the usage are like this. It can alert teams to potential absorption or bioassay liabilities. Then second use may be diagnose erratic bioassay results. Third use is given here, develop structure solubility relationship. It can use to select compounds for NMR binding and X-ray co-crystallization experiments. Then it can be useful in develop generic formulation for animal protein. So ultimately, it can be helpful in drug discovery. Thermodynamic solubility, when we go through the thermodynamic solubility, we can find the different uses like it can be helpful to guide formulation development like FND. Diagnose in vivo results. In vivo means when we go through the animal study, it can be in terms of in vivo results. and then plant development strategy. Then it can be also useful in file regulatory submissions. So these are the different aspects of thermodynamic solubility, which can be ultimately helpful in late discovery and early development. So this is the different. These are the differences between the different type of thermodynamic and kinetic solubility. Now, effect of solubility. So, as we earlier discussed, solubility is very necessary for a systemic effect or for a therapeutic effect or for a pharmacological effect of any drug. Because first, the drug, if it is present in solid dosage form, it disintegrate, then it dissolve, then it transfer to the membrane, and then it will reach into the systemic circulation. So solubility, then permeability, then metabolism. These are the different mechanisms can be occur during the transfer of drug through the systemic circulation. So low solubility limits the absorption and then it causes the low oral bioavailability. So solubility is very necessary or it is the one of the important requirement for substance to dissolve the drug or to make the drug more soluble, and we can ultimately increase the bioavailability of the drug if we increase the solubility of particular compound. So low solubility limits the absorption and causes low oral bioavailability, whereas the high solubility increase the absorption and causes high bioavailability. So you can see the picture here where the solubility, permeability and metabolism are related with each other. When we compare the different aspect of structural aspect of different drug, we can find that the antiviral drug like indinavir, where the first structure this is insoluble, but when we provide or when we go through the ionizable part of this drug, it is giving the oral bioavailability up to the 60% in human being. So these are the different examples which show the different solubility by different mechanisms. Now, after the discussion of different theoretical aspects regarding the solubility, the second part of this chapter is the quantitative approach to the factors influencing solubility of drug. There are so many factors. Some of the factors are already discussed, but we have to discuss about the particular type of solute in a particular solvent and how it is the related with the solubility mechanism. So now let us see the different factors which affect the solubility of drugs. So first we have to discuss about the solubility of solids in liquids. So there are so many factors which affects the solubility of solids in liquids. Like one is the particle size, surface area of drug particles. First factor which affects the solubility of drug or solubility of solids in liquid solvent is the particle size. If the particle size is reduced or decreased, then the surface area will increase and ultimately the solubility will be enhanced. So particle size can be reduced by the micronization process or by the combination process, and it will increase the surface area and ultimately the solubility will also increase. So you can compare the different diagrams which is given in section A and B. In A section, the before particle size reduction, the small surface area is given here, and after B diagram, after particle size reduction, increasing the surface area of drug solute. And when we go through the process or mechanism of solubilization, if we see in previous lecture, that first there is the creation of hole or cavity in the solvent molecules, then breakup of the solid particles, and then integration of the solid particles into the cavity of the solvent molecule. So these are the different three-stage mechanism for solubilization. So the size is reduced or if the surface area is enhanced, then the solubility will be the increase. So increasing the surface area of drug particle, we can increase the solubility of particular drug compound. Now, when we go through the equation, log S by S0 equal to 2 by 2.303 gamma V divided by RT small r, where the S0 is the solubility of large particles, S is the solubility of smaller or fine particles, gamma is the surface tension of the particles, V is the molar volume, T is the absolute temperature, R is the radius of the fine particle. And capital R is the molar gas constant. So this equation can be helpful to understand the relationship between the size of the particle then the solubility of the particles. So by going through this equation, we can predict the solubility of different size particles. Example is given here. The solid is to be comminuted. Comminuted means the particle size is reduced so as to increase its solubility by 10%. That is, S by S0 is to become 1.10. So what must be the final particle size, assuming that the surface tension of the solid is 100 dynes per centimeter and the volume per mole is 50 centimeter cube. The temperature is given as 27 degrees centigrade. So by going through the equation as we discussed, we can find out the final particle size in terms of micrometer. So it also show the effect of particle size on the solubility. Second important factor after the particle size, this is the molecular size. So molecular size will affect the solubility. The larger the molecule or higher its molecular weight, the less soluble the substance. So larger molecules are more difficult to surround with solvent molecules in order to solvate the substance. And if the interaction or solvation or degree of interaction is less, then the solubility will also decrease. So larger molecules are more difficult to surround with neighboring solvent molecules in order to solvate the substance. So ultimately, the solubility will decrease for the this type of molecules. In the case of organic compounds, the amount of carbon branching will increase the solubility since more branching will reduce the size or volume of the molecule and make it easier to solvate the molecules with solvent. So if the carbon branching is there, it also increases the solubility because more branching will reduce the size or volume of the molecule and make it easier to solvate the molecules with solvent. So interaction will be more easy and ultimately the solubility will be enhanced. Then the boiling point of liquids and the melting points of solids. So when we go through these different examples of boiling point of liquid and melting point of liquid, so melting point of solids, how it is related with the solubility, let us see in these examples. So these boiling point and melting point both reflects the strength of the interactions between the molecules in the pure liquid or the solid state. In general, aqueous solubility decreases with increasing boiling and melting points. So you can go through the different example and find out the solubility. Like N-pentanol, where the boiling point is given here 137.8 degrees centigrade and solubility is 0.26 mole per liter. Similarly, when we go through the 2-methyl 2-butanol, where the boiling point is less, it is given as 102 degrees centigrade and the solubility is higher 1.40 moles per liter. So when we compare the solubility values with their boiling point of particular compound, we can understand this concept easily. Similarly, in solid compounds like sulfadiazine, where the melting point is 253 degrees centigrade, solubility is given as 1 gram in 13 decimeter cube. And in sulfathiazole, where the melting point is given here 174 degrees centigrade, and the solubility is 1 gram in 1.7 decimeter cube. The next factor is after the different melting points and boiling point. The fourth one is the influence of substituents. This is very important factor. So on the solubility of molecules in water can be due to their effect on the properties of the solid or liquid. For example, on its molecular cohesion or to the effect of the substituent on its interaction with water molecules. So substituents can be classified as hydrophobic as well as the hydrophilic depending on their polarity. So as we discussed, life dissolves life. So depending on the polarity of the substituent group attached to the substrate, we can classify the substituent based on their polarity. It may be either hydrophobic in nature or maybe hydrophilic in nature. So you can see the examples here where the polar groups such as OH group capable of hydrogen bonding with water molecules impart high solubility. So OH group, hydroxyl group, which is the capable of hydrogen bond formation with water molecule, it imparts the high solubility, which is polar in nature. When we take the another example of CS3 group and Cl group, you can find that the non-polar groups like CS3 and Cl are hydrophobic in nature and they can impart low solubility comparatively. Then ionization of the substituent increases the solubility. When we go through the ionization of particular compound substituent, we can increase the solubility. Like carboxylic group COOH and NH2 are slightly hydrophilic in nature, whereas COO minus ion and NH3 are very hydrophilic in nature. So by ionization of the substituent, we can increase the solubility. Now, when we take the example of position of the substituent, it also affects the solubility. So, the position of the substituents on the molecules can influence its effect on solubility. For example, the aqueous solubilities of ortho, meta, and para dihydroxy benzenes. So, example of ortho, meta, and para dihydroxy benzene is given in this slide. So you can see here the solubility in mole per dm cube. So where the ortho is having 4 mole per decimeter cube, meta is 9 and para is having 0.6. So we can conclude that meta group having higher solubility than the ortho and para. So when we go through the question, like what are the differences in water solubility between resorcinol, hydroquinone, and catechol? So in ortho group, where is catechol is given 430 gram per liter is the solubility and melting point is given here 105 degrees centigrade, where the meta derivative like resorcinol, where the solubility is 1100 gram per liter at 20 degrees centigrade and melting point is 110 degrees centigrade, where the para derivatives like hydroquinone having the less solubility like 59 gram per liter at 15 degrees centigrade and melting point is 172 degrees centigrade. So the solubility is high, very high in water. So the beta derivative is more asymmetric and it will give a more stable crystal structure. This explains the high melting point and the low solubility of para derivatives. There is a small difference in melting point of two other derivatives like ortho and meta, but a substantial difference in solubility. So most likely intermolecular hydrogen bonds in the ortho derivatives play a vital role. These will be in competition with the hydrogen bonding with the solvent and then also affect the solubility. And maybe molecular symmetry is involved in the low solubility of hydroquinone and intra-hydrogen bonding is the region for the lower solubility of catechol compared to isocinol. So when we go through the different ortho, meta, and para derivatives, we can deduct the solubility of different compounds with their melting points. The lowest melting point of orthoisomer is due to intramolecular hydrogen bonding, whereas meta and para isomer possess intermolecular hydrogen bonding, and thus they have higher melting points. So when we go through the another Example, the para-dichlorobenzene has higher melting point and lower solubility than those of ortho and meta isomers. So when we discuss this example, we can see that the para-dichlorobenzene is more symmetrical in nature than ortho and meta isomers. So for this reason, it fits more closely than the ortho and meta isomer in this crystal lattice. So therefore, more energy is required to break the crystal lattice of para-dichlorobenzene. And due to the more energy is required to break this crystal lattice of the para-dichlorobenzene, so as a result of this, para-dichlorobenzene has a higher melting point and lower solubility than ortho and meta isomers. Now, next one is the very important factor. This is the temperature. So, at the expression of solubility or at the time of result of solubility determination, we have to mention the specific temperature. So, the temperature having very important role with the solubility. So, temperature will affect the solubility. If the solution process absorbs energy, then the solubility will be increased as the temperature is increased. And if the solution process releases energy, then the solubility will decrease with increasing temperature. So generally, an increase in the temperature of solution increase the solubility of solid. So in case of solubility of solids in liquids, we can increase the temperature. So ultimately, we can increase the solubility of particular solute. Few solid solutes are exemption of this word because they have the less solubility in warm solutions. For all the gases reverse to this solid in liquid, solubility decreases as the temperature of the solution increases. Now next property is the crystal properties. So crystal properties also affects the solubility of particular compound. They are polymorphic crystals, maybe solvates or amorphous forms. Polymorphs, as we have know that the same chemical structure but different physical properties such as solubility, density, hardness, and compression characteristics. So a drug that exists as an amorphous form or non-crystalline form generally dissolves more rapidly than the same drug in crystalline form. So we can say that the amorphous form having the more solubility than the crystalline form of a particular drug. So this is the crystal property which also affects the solubility of particular drug. Now next one is the very important parameter which is known as pH. So pH is the negative logarithm of hydrogen ion concentration. And it is the one of the primary influences on the solubility of most drugs that contain ionizable groups. Large number of drugs are weak acids or either weak bases. So solubility depends on the degree of ionization. And degree of ionization governs by the constant ionization constant, which can be represented by pKa. Degree of ionization depends on the pH and pKa values. So about 85% of the marketed drugs contain functional groups that are ionized to some extent at physiological pH within the range of 1.5 to 8. When we go through the different examples, like carboxylic acids containing more than 5 carbons are relatively insoluble in water. They react with the sodium hydroxide, carbonate, and bicarbonate to form soluble salt. So when we take the example of like stearic acid, which is practically insoluble in water, but when it reacts with the sodium hydroxide, it will form the sodium salt like sodium stearate, which is readily soluble in water. So as the number of carbons in a carboxylic acid series becomes greater, the boiling point increases and the solubility in water decreases. So carboxylic acid with 12 to 20 carbon atoms are often referred to as fatty acids. And fatty acids containing more than 10 carbon atoms form soluble salts with the alkali metals. And they are soluble in solvents having low dielectric constant. Like oleic acid, it's insoluble in water, but it is soluble in alcohol and other solvent like ether. benzoic acid, which is soluble in sodium hydroxide solution, phenol, which is a weakly acidic drug, only slightly soluble in water but quite soluble in dilute sodium hydroxide solution. So organic compounds containing a basic nitrogen atom. So most of these weak electrolytes are not very soluble in water but are soluble in dilute solutions of acid solvents. So when we go through the relationship between the solubility of an acidic drug to the pH of the solution, we can express these relationship with the help of Anderson-Hazelbeck equation. So for acidic drugs, it is written like pH equal to pK plus log S minus S0 divided by S0, where S is the total solubility of the drug combined in anionized form with ionized form, and S0 is the solubility of the unionized form of the drug. So pH is the pH below which the drug separates from solution is the undissociated acid. So with the help of this Henderson-Hazelbeck equation for acidic drugs, we can calculate that if the pH of the solution is known, then we can calculate the solubility of acidic drug at a particular pH. Minimum pH that must be maintained in order to prevent precipitation from a solution of known concentration. So these important informations can be calculated with the help of Henderson-Hazelbeck equation for acidic drugs. Similarly, for basic drugs, it is written like pH equal to pK plus log S0 divided by S minus S0, where S is the total solubility of the drug, combined the unionized form plus ionized form, and S0 is the solubility of the unionized form of the drug. And this pH is the pH above which the drug begins to precipitate from solution is the free phase. And Anderson-Hazelbeck equation for basic drugs or alkaline drugs provides the different information. Like the pH of the solution is known, then we can calculate the solubility of a basic or alkaline drug at a pH. A minimum pH that must be maintained in order to prevent precipitation from a solution of known concentration. So these are the different ionization of drug. If we discussed about the Henderson-Hazelbeck equation, so pH equal to pK plus ionized drug divided by unionized drug for acidic substances. And for alkaline drug, pH equal to pK plus log ionized drug divided by ionized drug. So these are the Henderson-Hazelbeck equations. So we can see here, these are the different Henderson-Hazelbeck equation, which is already discussed for weak acid and whereas for the weak alkaline substances. And these are the different examples are given here. You can go through these numericals and solve it. Like what is the pH below which sulfur diazine pK value is given here 6.48 will begin to precipitate in an infusion fluid when the initial molar concentration of sulfur diazine sodium is 4 into 10 to the power minus 2 mole per deciliter cube, and the solubility of sulfur diazine is given as 3.07 into 10 to the power minus 4 mole per dm cube. So the pH below which the drug will precipitate is calculated using the Henderson-Hazelbeck equation. So you can put the values and find out the answer of this numerical. Then ionization and pH. If we discuss strong versus weak acids and bases. So strong acids or bases are ionized at all pH, where the weak components are only ionized at certain pH. And most drugs are weak acids or weak bases. Ionized drugs are not very lipid soluble, only non-ionized form of drug crosses membrane readily. Then percent ionization is pH dependent. Ionization constant pK is the negative logarithm of the ionization constant and is equal to the pH at which a drug is 50% ionized. Weak acids become highly ionized as we increase the pH, and weak bases become highly ionized as we decrease the pH. So these are the different relationship between the pH and ionization, which can ultimately affect the solubility of particular compound. So these are the different ionization ratios we can calculate or compute with the help of Anderson-Hazelbeck equation as we discussed in very detail. Now, when we take the example of percent ionization of drugs, we can find the different weak acid and the percentage ionization and weak basic and the percentage ionization at particular pH. So this is all about the percent ionization of different drugs at different pH. So when we go through the summary of today's lecture, we can discuss about the what is the significance of solubility and what is the effect of low solubility or negative value or less value of solubility of for a particular compound. Then we discuss about the what are the different factors which affects the solubility of solids in liquids with different examples. Then we also discuss about the association, and then we discuss about the different solubility parameters, Hildebrand solubility parameter in our today's lecture. And lastly, we give the examples of different pH, relationship between the pK and then ionization of different drugs. You can go through these references and read out more material regarding today's topic. Now, when we proceed our today's quiz section, we can find these questions like the what term is given to a substance that can dissolve in a particular liquid, like insoluble, soluble, insoluble. You can correct. You can take a correct answer. In a second question, in a solution, what term is given to the liquid, like solute, solvent, and reagent. The third question is given here in a solution, what term is given to the solid that is dissolved. A option is solute, solvent, and reagent. And next one is the which of the following is a typical unit of solubility? Like A is given a gram per dm cube, mole per dm cube, and gram per 100 centimeter cube. So you have to give the correct option for this question. The next question is given here. Why is it important to for solubility at a given temperature? So we already discussed the significant effect or significant role of temperature regarding solubility. So a option is given here. Some substances only dissolve at low temperature. Some substances only dissolve at high temperature, or solubility depends on temperature. Next question is which has more carbon dioxide dissolving it, like warm lemonade, cold lemonade, and cold lemonade. The next question is what will happen to a hot saturated solution of copper sulfate if the temperature decreases? The solvent will evaporate, the crystal will form, or it will turn colorless. So you can correct answer. Next one is the for most solutes, what happened to the solubility is the temperature increases. So what will be the effect of temperature on the solubility of solids in particular solvent? A option is solubility increases, B solubility decreases, and C is the solubility stays the same. Next one is the for most gases, what happens to the solubility is the temperature increases. So like solubility increases, the solubility decreases, or the solubility stays the same. So what will be the effect of solubility is the temperature increases for the gases. So you have to go through the reading material, or you can go through the today chapter and find out the answer of this question. Then the short answer type of question, two questions are given here. One is enumerate the factors affecting solubility of solids in liquids. So we have to give the different factors as we discussed in our today's lecture. Lastly, give the significance of solubility phenomena. So what is the overall effect or significance of solubility in different pharmaceutical process? So we have to give the answer with suitable examples. So this is all about today's lecture. So please go through the chapter reading material and find out the different aspects regarding the solubility. Thank you all.